Hey there YouTube, this is SGM4306 and I'm trying something completely new. It's about 2:30 a.m. Can't sleep. I thought I'd do a very quick tutorial, especially since it's relevant to the digital clock that I made using this display that was donated to me by IC Station. And this guy communicates over a serial peripheral interface, or SPI bus. And so I'm going to show you guys today how to actually softcore program one, just using software, no extra hardware necessary, using the GPIO on this chip here, which is a PIC 12F629. And I'll be using a PIC 2 to actually program it. And after we're done, I'm going to actually plug this into my logic analyzer over USB and show you guys the signaling and that everything's working. So you can use this for a lot of different chips that you end up using either I2C or SPI. This will be just a quick tutorial on SPI since I think it's the simplest protocol that you could actually communicate serial over. So hopefully you guys will forgive. I'm still figuring out screen capture situation and audio and whatnot. And so there's going to be a watermark here because this program that I found for free has a watermark. So hopefully that's not an issue. I'll end up finding a better way of doing this anyway. So I'm using MPLAB IDE version 8.92. There's a newer version called MPLAB X. It's functionally the same, just the buttons might be in different places, but all the general commands are going to be the same. So all I ended up doing here was creating a project, going to Project Wizard, and then I select the proper device, which is the 12F629, and I'm using the High-Tech C and C compiler. And so we'll be coding in C. I created a new folder and I just went through this and created the folder. I called it PIC 12F629 soft SPI. And within that I opened a new file here and just named spi.c. And then what you're going to want to do is go into project, add to project, and then point it to that folder. And that just opens up a prompt. And once you do that, it'll be added to the project folder. So once we go to compile this, it'll be able to find all the files, and you're good to go. Another thing that I did was select programmer, and I selected my PIC 2, and then finally under configuration, I double check to make sure that the device is the correct one here. Once that's all set up, we go into configure and configurations, and then I'll open this window here. And configuration bits, I disable setting it in my code, and I want to set it via the GUI here, just because it's easier to I don't remember all the register names. It's easier. Anyway, so I set the internal oscillator with the IO function on GP4. I disable the watchdog timer. I disabled the power up timer. I set GP3 to digital I/O, and basically the reset line on the microprocessor is internally tied high, so as soon as we give the chip power, it'll start executing the code basically. So these are the steps that I take so that every time I can get it up and running without little things bogging me down and the chip not working and I can't figure out why. So next up, disable brownout detect, and make sure program code protection and data memory code protection are disabled as well. And once we get this done, I include a file called pic.h, and that includes all the pin definitions. So I can use short name terms for all the pin names as opposed to doing a port addressing. So this just makes it easier, so I don't have to refer to kind of like the hexadecimal address. I can just use kind of the name of the pin as given by the datasheet. And so here, after I do that, I create essentially a function called main. And actually, this doesn't even have to have a return type. Let's just do void. So main is basically where your code, the main body of your code executes, and this will execute over and over again so long as you don't stop it. So what we are going to do, just as a sanity test, is just code a LED blinker and get that working first off and make sure everything works. So let's just see though, before we type anything else in, if this will actually compile, if we have everything set up correctly. So we're just going to hit this button right here and this will compile it. And you can see build successful, using up 8 words of my 1 memory. So basically this just means that everything works. It'll compile successfully as long as I don't make any coding mistakes. So next, let's just code a simple blinky. Okay, so we're going to do a blinky. So let's put an infinite while loop in here. I'm very pedantic about my indexing and spacing and whatnot, so just bear with me. So anyway, within this while loop, we are going to want to, here, let's make our lives easier. Not yet. So we're going to use GPIO0, say, why not? And we're going to set that high. Let's make a delay function. We haven't written it yet, but let's put that in there, and then GPIO0 equal low. And then put another delay. So what I'm doing here is I'm turning on one of the pins, which is labeled GPIO0, and we'll look that up in a second on the data sheet. We're going to make a delay function, so it'll wait a little bit, and then it'll turn off, wait a little bit again, and then it goes back up to the beginning of the while loop, and then keeps doing that indefinitely. And this is to make sure that we set our configuration fuse bits correctly, so that the processor is actually running, so we don't have a problem where we're trying to debug a processor that's not actually running. So in order for this to work, though, we're going to need to make a delay function. So I'm just going to make a delay function here. So we are going to do, let's just do int x equals, well, let's just make it long. So this data type that I'm setting to long is because I want to set a value that's actually pretty large. And we're going to see in a second exactly why. If I set this too small, then it would blink so fast that our eyes couldn't see it. It would look like it's always on. So in here, you can use a for loop. I like while loops for some reason. I don't know. It functionally gets compiled to the same assembler anyway, so it doesn't really matter. So while x is greater than 0, we're just going to do x minus minus. And what this means is basically decrement x. So x equals x minus 1. So every time it goes through this while loop, it subtracts 1. And when it gets to 0, then it finally can exit, and then it'll go back to our code. So this will allow me to insert a small space in between. So let's compile this and burn it. So I'm going to build, make sure it goes through successfully. Okay, and we can see how much memory we're using. We're barely using anything at all. It's a very simple programmer. Now we're going to want to click this. Once we make sure our PICKIT2 is plugged in over USB, we establish a connection, and we're ready to go here. So now we can just click program. And now we're ready. So it successfully programmed the chip. And so now I'm going to grab an LED, pause, and bring up the data sheet and show you guys what pin we're actually going to connect to. So give me a second on that. We can see here, well, I grabbed an LED. I'm not going to use a current limiting resistor. This is just for quick debugging, so it's going to be fine. I'm going to lower the supply voltage also on the chip. So this is the chip that I'm actually using, and I already have it wired up for VDD and VSS for ground and supply, so it's going to be supplied power via the USB connection. And we're looking for GPIO0, which is the 7th pin, and we want to take a wire as well. So all I'm doing is going to the 7th pin, hooking up an LED, the positive side, and then on the other side, taking a wire to ground. And I'm just using any old bit of wire that I have. Actually, yeah, VSS, I do not need a wire, I just realized, because they're right next to each other. So pin 7 and 8 go to the LED positive and negative respectively. So now I have an LED plugged in. Okay, so in my excitement, I found something very important. We need some configuration for the microprocessor first. So for now, I'm just disabling comparators. We're not doing anything with analog sensing or anything like that, so we don't need them. And for the tri-state input-output, we need to set which pins are going to be outputs. So for now, let's just set all the pins to output. Despite there is a caveat to this, but we're not going to actually run into it for now. So, I additionally decided to actually use GPIO2 because one is actually used for the programming interface. So if we put an LED on that, we could program it and then run the code, but we would not be able to actually reprogram it the second time without unplugging the LED each time. So that's going to get annoying, so I'm just going to use a free pin, which is GPIO2. So let's go through, compile, and program. And we're good to go. So let's see. LED turns on. I might have set that delay a little bit too long. So you can see it's flashing very slowly. Say I want to increase it by a factor of 10. Refile. Reprogram. And there you go. You can see our blinky is working. So now that we have that up and running, I'm just going to pull out the LED. We do not need it anymore. This was to test. So I'm actually going to comment this out. This will be our sanity test. If something breaks, we know where to go back to. So let's just make a very simple function called SPI. It won't have any return data. SPI. And we can set it, let's do an 8-bit SPI transfer. We can make the SPI transfer as long as we want, but we don't actually need any more than 8 bits for the purposes of this demonstration. A lot of devices are 8-bit transfer anyway, and it's easy to make it 16 or whatever you want. So we'll call this char byte. So byte is the variable that we pass to this function called SPI, and whatever byte is, it sends out serially. So we'll just save that, and so to make our lives easier, we will define some pins, and this will just make it a little bit easier. So now we can see side by side. So let's use GP2, GP4, and GP5. One caveat is GP3 can only be used as an input on this particular chip, so we cannot actually use this as an output, unfortunately. And as I said, I don't want to use 6 and 7 right now, pin 6 and 7, which is GPIO 0 and 1, because those are the programming pins, so I'd have to keep disconnecting my programmer every time I wanted to test it. So I'd rather not do that. So let's get this set up. Okay, so let's define latch, and this will be GPIO 2. Let's define clock. That will be GPIO 4. And then finally, let's define data. And these are all standard terminologies for, and this will be GPIO 5. These are all standard SPI terminologies for the pins. Some of them we'll call latch CS, which is chip select, but they're the same exact function, just they call it a different thing. Let's just save and make compiles. Good, so we're good to go. So now whenever we use the word latch, it'll replace it in the code GPIO2. So this will make our code a lot easier to debug, because as a programmer, it's a lot easier to know what latch means or data or clock than GPIO2 or 4 or 5 or 6 or whatever. So this will make it a little bit easier. So here, what we are going to do is most SPI devices will actually hide a low. So let's just open up a tab here, and SPI, see if we can find a an image of how it looks. Okay, so like this is a good example. So there are different polarity you can use, but without making it any more complicated, let's just use on the rising edge, the data is triggered. And you can ignore the MOSI MISO. Basically, this is for bidirectional data, so sending it from one device and then back and receiving it. We're only going to be writing a SPI transmit function right now. So, because the LCD that we're using, we actually don't strictly need to read data back from, so we actually don't need that separate pin. Anyway, so one thing to note is this SS is actually the latch in our case, and it idles high. So whenever the chip's not talking to anything else, it needs to be high. So what we are going to do is just to make sure, So we said GPIO2. So basically from right to left here, so this is 0, 1, 2. So the third bit in, let's just initialize that to high right now. And so that'll make sure that it's always, as soon as a chip starts up, it's always high. And I always like, just to be sure that I know what's happening, is I'll set it high at the beginning of my function in case something else got interrupted or forgets. So it'll be high for now. So next up is just to make sure everything's in a known state, we'll also set clock equal to low. We're just following this diagram. So next, why not just do a for loop? So for, we'll use an integer I for the counter value, and we'll initialize that to, let's actually do, well, fine, 0. And then we'll do while I is less than 8. So this will send 0 to 7, so it'll send 8 bits or a byte. And then finally, we want to do I++, which means increment I every execution of the loop. So this will execute 8 times and then X out. Now we have to care about the end settings. So after it's done, what we actually want to do is make sure clock is low again, and then make sure finally that latch goes back high. Now before we start communication, we should have data in a known state as well. So we'll just initialize that to low, and then finally, right before we enter that for loop, we will switch latch to low, which means start sending data, which is basically this falling edge here. And so this should set everything up. And once again, after it's done, just to have it as a known state, we'll set data equal to 0. Let's save in the file, make sure we didn't make any errors. We're good. So now within this for loop, what's going to be happening is we're going to be toggling this S clock from low to high. Well, we call it clock. So let's just put in clock equals 0, clock equals 1. A lot of this is redundant because we're actually setting clock twice in this case, but it makes it a little bit easier to see what's happening if we're very strict in the way that we program and following a diagram exactly. So for starters, this is a good way of getting something to work. You can always optimize in terms of speed or whatever you want later on. So now we have a rising edge on clock. So in between when we set the clock low and then we bring it high, that's when we actually want to set the data so that it's at a known value at the transition point. So we can set data equal to, and we are going to want to grab a specific value of byte. So let me bring in a helper function essentially to help us out with that right now. Up at the top, I'm going to kind of do something a little bit sneaky. I'm going to use, it's really a function. This is actually kind of a declaration. So in the same way we defined a pin and tied it to like a name, a label, I'm going to create kind of this function that whenever you use this test bit, you give it like a byte, for instance, and what bit number that you're actually trying to access. So here within data, because we're only sending one value at a time, we're not sending the whole 8 bits at once. We only need the ith bit right now. So under data, we can do test bit, and we want to pass a byte. A byte is the value that we're intending to send, and that is the argument that we're passing to the function SPI. So now we're going to send it the whole word byte, but we only want one value. Since data is one pin, it can only be a 1 or a 0. So we want to send it the ith value, for instance. So this will actually, if our word is 0, 1, 1, 0, 0, 0, 0, 1, for instance, where this is the least significant bit and this is the most significant bit, we'll be sending 1, and then the next turn 0, 0, 0, 0, 1, 1, 0, exactly like in this image. Once we do that, we should all be set to go now. So let's just save, build successful, program. Okay, we're all good to go. So now let me pause the camera and get set up, actually hook this up to my logic analyzer, and I'll explain to you guys how exactly that works and show you guys it working. With everything more or less set up, now the only thing left to do is actually call our function. So we'll call SPI, and then let's just send that 0, 1, 1, 1, 2, 3, 4, 1. So this should be 8 bits. Okay, and let's just define that as a binary value. And we'll save, compile, and good to go, program the chip. We're only using 63 words of memory and 4 bytes of RAM, which is really nothing, but it adds up quick. This is a very simple program. So I have a logic analyzer here actually, and that's this guy. It's just a cheap eBay, but it does its job. It's an 8-bit logic analyzer, and it just hooks up over USB. And so we have it hooked up. It's powered on. We heard Windows, well, I heard Windows make a sound. And so, install something. Great. So yeah, give me a second while that installs the driver. Okay, so as you can see here, it shows up as a Soleil Logic USB Logic Analyzer. This is it's a little bit iffy. This is a clone Logic Analyzer. The legitimate one is much nicer, well worth its weight in gold. But this one was a lot cheaper and I could actually afford it. Anyway, what we're going to do is open up this software, and this has detected our device right now. So I'm going to label this latch. This was clock, I believe, and this will be data. So we're just going to go and we're going to compare it to the actual signal there. It's going to be triggering on the falling edge of the latch, so that should be okay. And we're just going to hit start, and there we go. So now we should something. Latch is originally high, it falls, it goes low for the duration of the transfer. You can count how many rising edges, 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 bits transferred. See here, on the first rising edge, the data is high. On the second one, it goes low. If you were actually to zoom in, it looks like it's high, but that's just kind of because we don't add any delays in. If you were to actually zoom in, and you can see it's clearly 0 when this goes high. So this works. It's not exactly symmetrical like this, but this will be accepted properly on SPI bus. So it goes 1, 0, 0, 0, 0, and then 1, 1, and then finally, let's see, last one would be here, 0. So that's exactly what we wanted it to do. So we were able to transmit a byte. We can easily go back to our code, this guy here, and we can change the value that we want to set. So now let's just send 10, 10, 10, 10, 10, 10. Hit file. Program the chip, and go back there. Rerun this. Now we can see a byte consists of, it's actually reversed, but it is from right to left, 10, 10, 10, 10 over here. So that's exactly it. So now we're able to send any single byte that we want. So this could be used for devices like serial LCD displays, graphical or not graphical, or MSEQ makes a graphical audio analyzer that uses a serial protocol as well. So we can use all this in order to control different devices like that, or something kind of like one of these displays. This display actually uses I believe it's like a 16-bit transfer or something like that. So we would need to extend our code by increasing this count value in order to send more bits, essentially. But other than that, this is basically how to program an SPI transmitter. To do a receiver would be pretty simple. Just instead of writing to data, you would actually be reading from it as an input, not an output. We can cover that in a future, lecture or whatever you want to call this. I just thought it'd be kind of cool to show you guys generally how to program up and running from scratch. So yeah, if you guys are programming something and you want to use a software SPI instead of hardware, this way I can always change these numbers around. So the good about microprocessors is encoding software-based communications. I can label these any pin that I want, so long as it's physically on the chip and it's available as an input or output. Then I can change these numbers, and that way I can actually optimize my circuit board layout because it's not constrained. Then if two wires would be crossing, I can just switch them in code to make the board layout a lot smoother, so everything's all your ducks are in a row. So that's one of the benefits of using a software peripheral like this. The downside, obviously, is it has to sit there and toggle the actual pins, and that consumes clock cycles. Whereas if you're using a hardware SPI, you would just give it the byte and it would transmit on its own, and your processor can go and do something else. So there's some pros and cons to this. I just wanted to show you guys how you set something like this up pretty quickly, and it only took me, I don't know, about half an hour or so, probably after editing this video down. But anyway, hopefully you guys like this video, and if you want to see something more like this, or hopefully that the text that's showing up in the middle of the screen didn't block anything, I had to figure out maybe a better free screen capture program. If you guys have any suggestions that doesn't do any time limitation BS or inserting images on the screen while you're filming, that would be great. So yeah, I'll see you guys next time. Bye.